Welcome to the SEI podcast series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense and operated by Carnegie Mellon University. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts. My name is Suzanne Miller. I'm a principal researcher here at the SEI, and today I'm pleased to introduce you again to Dr. Julien Delange, who has been a guest on our audio podcast series many times. This is his first time on video, so you get to see what Julien looks like. And he's talked to us about his research in the past about the Architecture and Analysis Design Language, AADL, which is very popular in Europe. It's very popular here in the avionics industry. And today he's going to be talking about his work on a project related to that known as Effective Reduction of Avoidable Complexity in Embedded Systems. And the acronym for that is ERASIS. So we'll be talking about ERASIS, but let me introduce him a little further. He is researching here at the SEI. His work focuses on system and software architectures, especially in how you can model those with things like AADL. And prior to joining the SEI, he worked as a software engineer at the European Space Agency. So thanks for coming back and talking to us some more, Julien.
Thanks for having me, Susan.
So we know that systems that run avionics, aerospace, automobiles, medicine, they're all made up of lots of different software and hardware components. They're executed on different components, and they're interconnected using various buses and protocols and different ways of getting messaging going. So let's talk about complexity in embedded systems and what is it in particular in relationship to models, architecture, systems that gives us a problem with that.
So first of all, you have to consider the complexity we have and that increase over the past years. So let's take an example that is really simple and everybody can understand the problem, the underlying problem. 10 years ago, your car has like a couple of ECUs, electric control units,
right,
in your car. And maybe you have like three buses to connect them. So for example, the entertainment system, the brake control, some basic
climate
function.
control.
Exactly.
Right.
But right now, your car probably has between 50 and 100 ECUs and up to 7, 8, or even 10 buses. And if you look right now, how many problems we have, not only with cars, but what we call the Internet of Things.
Things, yes.
Everything is interconnected together. So in fact, you have more software, more processor interconnected, and you have a lot of complexity. Think about the TCP/IP stacks. We have bugs in this stack, and you can exploit that, and you can after that attack the system. For example, in all the Internet of Things systems connected in your home, every day we hear about
some kind of intrusion.
Exactly, a safety defect and this kind of thing.
Yeah.
Because it's getting really complex, and also we have to use really some safety and good design techniques, and we don't do that.
And we also. It's not just the developers, it's on the user side as well. Yeah. We've all heard about the example where somebody has a router and the password is password and nobody ever changes it. And so that provides an intrusion point that a developer doesn't expect to be there, and it shouldn't be there, but It is there. And so if it's there, so that's a complexity, an added complexity they were not accounting for that allows a vulnerability to occur and an intrusion eventually.
So this complexity, for example, the password thing, is something that is pretty simple to mitigate. I mean,
in comparison to other things,
exactly.
Yes.
So for example, the password, you can ask the user when you install your router, change the password, and have a way to force him to change it.
Right.
But there is something that, for example, it's a design, it's an architecture issue. For example, if your car is connected to the internet and the brakes are directly connected to the internet, there is a design issue. Your braking system, your critical function doesn't have to be connected.
I don't want my brakes connected to the internet.
But in some system, you can have this kind of thing.
Yeah.
So let me step back a little bit. We have two different kind of complexities. What I will call the avoidable complexity and the essential complexity. So the essential complexity is we have more and more function on your system. So we have to design these different functions. We have to have this function on your car.
We have to account for them.
Exactly. But the avoidable complexity is the way you implement the function, the way you design your system, it will incur complexity. And we want to reduce and avoid this complexity. We want to mitigate it.
Gotcha.
We don't want to have it. Because on the long run, this system has to be maintained for 10, 20, 30 years.
Yeah.
And we don't want to maintain
it. And there's so much complexity that's essential. We don't want to add that extra layer of the avoidable if we don't have to.
Exactly.
So that's what we're trying to get at.
So in fact, in this project, what we did is to have a measure of complexity to see exactly how you can measure complexity and what is the impact on the long term. So for example, we see the impact on the development effort, but also in terms of money. Because, I mean, when you develop the system, it's going to cost more, but as I said, your system will take, you have to maintain for 10, 20, 30 years.
Right.
And we find out that, in fact, on the long run, having a system that is really complex can really increase the cost.
It makes it very fragile.
Exactly.
So for sustainment purposes, we lose sight of what decisions we made. We lose sight of what somebody over here did to this bus, and I've never worked on that bus. So all of these kinds of things make the sustainment problem even more problematic when you have complexity that is essential and avoidable.
Let me give you just an example about the impact of complexity. Really simple. Take a plane, a car. You have to test this system. You have to certify this system. So the more complex your system is, the more difficult it is to test it, to certify it.
Yep.
So in the long run, when you have to recertify the system, it's going to cost you more.
Yes.
And then you know better than anybody else that certification is really costly.
Very costly, very time consuming, and just small changes. That's the thing with complexity. You can't always see the effect. You see a direct effect, but with complexity, we're trying to look at the indirect effects as well. And those indirect effects are what we call them cascading effects many times, are things that we have to account for in testing and recertification.
Exactly. So the idea was, let's step back, have a look at the design artifacts, the models, because right now safety critical systems are designed using models, and try to find the complexity when you design the system. So this is what we did. So what we did is we made two tools. One that deal about complexity with functional system, with SCADE. So SCADE is the modeling language used to design many safety critical systems.
Yes.
For example, the 380 plane and the
Airbuses 380.
Exactly. The ones that go from JFK to Paris.
Yeah.
And the 350s are designed with SCADE. Also, they are using it for some military application, medical application, and things like this. So we made a tool to be able to qualify and quantify the complexity in SCADE models. But also, this is a really emerging topics because right now, the industry is trying to adopt modeling tools.
Right.
So they just have to have a look at what complexity means for a model. So we did that, and also we designed a plugin for AADL to try to find some complexity measure in architecture model. But again, this is really an emerging topic because people just start to adopt architecture models.
And so so you've got two things that are happening together. You've got people introducing complexity just because they don't know how to model yet. And then you also have complexity that is introduced because it's needed by the design to affect the functions that are intended.
The first one.
So,
something really interesting is right now the industry is moving towards modeling-based engineering design.
They need the abstractions. It's too complex to try and keep all of this stuff at the code level.
But we find out that training is really important when you make the move. We made a study to see how people perform and how people are good at modeling techniques. And we find out that people with a good experience in software engineering, with C, Java, C++, whatever, they have a really hard time to use model-based techniques because it's new. It's really new. So we try to have a sense about how difficult it is. And in fact, training is really important because people have a really hard time to understand the logic of model?
Well, so I actually, you're not aware of this study, but several years ago, some colleagues and I did a study on modeling, the adoption of different kinds of modeling techniques in the software engineering community. And the basic finding of it was that software engineers tend not to use modeling unless they feel that they can't hold it in their heads themselves. Yeah. And by the time you get to that point, you are at a pretty high level of complexity. So now I do have a challenge in making them able to actually use the models in a productive way. So I completely resonate with what you're talking about.
This will be the challenge in the next year, being able to get engineers trained and to be able to understand exactly the logic and how to use the tool.
Right.
And it's going to take a long time.
It's one of the transition challenges, and that's one of the things that you and I and Peter Feiler, who's been leading this for a long time, have all talked about. Exactly. Transition challenges on this. So the tools that you are describing, where are they available to people? How can they access them if they want to try this out and see how difficult it is for them to use these?
So first of all, the goal as an FFRDC, what we want to do is to help all the people that are doing safety-critical systems and provide the tool for free. So what we did is we released the tool online. The Software Engineering Institute has a GitHub account, has a GitHub area on the web. So we released the source code on this GitHub repository.
So we've got the SEI GitHub repository is the place to go for that.
Exactly. So the source of the...
and we'll make that link available in our transcript so people can go ahead and get to it.
And so the tool for the ADR-related plugin are available. The one for SCADE is available with the documentation. Also, we have video online that explain on the SCI YouTube channel that explain how to install the tool, how to use the tool. Good. Last thing that is kind of important and to see how the industry is really interested in that topic is ANSYS, the tool vendor of SCADE, take our tools and evaluate the matrix. And they have an idea about using the matrix for their own tool.
So they want to evaluate the complexity of their own tool as part of...
Have some measure of complexity inside the tool.
Gotcha.
Like having a dashboard about complexity of the models and stuff like this.
So in real time, you can get clues as to whether or not your model is increasing. So this is a goal out of the range that you want it to.
So this is a goal at the SCI is to transition the work. So we did some research work, and right now we are trying to transition this work to the industry. So it was a really successful project from that perspective.
But now is the next step to actually build some of the training needed, or are you looking for industry to build the training?
Right now, so also this work has been presented at the SCADE user conference last month, and we see that there is a lot of interest. There was, in fact, a roundtable about model complexity and how to measure complexity. So we presented our tools, and I think right now it's also the turn of the industry to pick the work, see how they
and evolve it.
Exactly.
Because the thing about measuring anything like complexity, we have some of our listeners will be familiar with things like McCabe's complexity is a tool that's been around for decades that measures a certain type of complexity, but it only does one type of complexity. And when we're talking about communications, networks of interconnected things, there are lots of different aspects to complexity. So the tooling and the measures are likely to evolve as people understand better what kinds of things actually affect complexity and which ones are avoidable.
Exactly.
So very good. So what will you be doing next? You've got this tool out there, and so now what's next on the avoidable complexity kind of horizon?
So right now on the avoidable complexity, we try to transition the tool and have some discussion with the industry to see how they are using the tool, how it can be transitioned or not. There is a really big question right now is if we need new metrics. For example, we try to apply McCabe, ALSED, all the new metrics to this modeling environment, and to design also new metrics that are really specific to the modeling language. And so what we want is to have some feedback and have also some measure about what threshold is important or not. So for example, what complexity value means that your model is good, bad, what aspect you have to change
But some of that has to be context dependent.
Exactly.
Because if I have something that's a relatively closed system, I can probably tolerate more internal complexity. But if I have something that has many, many external connections, the simpler the individual components are, the better it's going to be in terms of. So it's not an absolute number that you're going to be able to apply and say this is good and this is bad.
Exactly. So it's really also context dependent.
Yeah.
So what we wanted is to have some people in the industry to take the tool and give us some feedback about the value and what metrics make sense or not.
Excellent.
This is really what we wanted. Also, right now we are also working on a topic that is kind of related, is how to have some measure of security from architecture models. So generate some
security is important when we start doing this Internet of Things. And it both increases complexity, but some of that's not avoidable. Because if we allow intrusion, then all kinds of things go wrong. So
this is we're working on this project right now. It's a 2-year project. It started last month.
Okay.
So we have some time.
Oh, okay.
We will design.
We'll have to look in on you in a year or so and see how you're doing with that.
Come back in 3 months.
Oh, okay. You're moving quickly. This is good.
I'm trying.
All right.
But we will have some measure about security in architecture models, for example, to automatically generate the surface attack, some security tests from the architecture, have what we call the security impact analysis. Is for each component you can see the impact if you have a security issue in the component.
Okay. And what it impacts besides that component.
Exactly.
The model allows you to see the effects that get propagated.
So let me give you a really simple example, really basic, and everybody can understand this example. Your phone can control, for example, your house.
Yes.
Lights and doors and lock and stuff like this. Imagine that your phone suddenly is compromised. Then maybe somebody can take over your phone and then control your house. So you see that a security in your phone can affect your house.
Right.
So the propagation of a security issue on the system.
And these are things that models help us to see more easily than if you're going through pages and pages of code. So that's one of the reasons we do the models. So you are continuing to do good things for us in this arena, and I hope all of you heard the call to action to please go out, find these tools on our GitHub, and provide some feedback if you get a chance to use them, especially on whether you see the measures of complexity that are being provided as being useful to you in your own analysis and design. We hope that you'll be able to do that. And I want to thank you for joining us today. There are several blog posts for those of you that are not already familiar with AADL, the Architecture Analysis Design Language, and there are blog posts on the two tools that we've just been talking about. So insights.sei.cmu.edu is where you would go to find links to the tools, and we will be providing some in the transcript of this podcast as well, which is available at sei.cmu.edu/podcast. Thank you, Julien, and thank you all for listening.